The plan for this lesson is to discuss how to compare two probability distributions using the Kullback-Leibler divergence. The KL divergence measures the difference between two probability distributions over the same random variable, and it has an information theory interpretation. So, given two probability distributions P and Q, KL divergence measures the information lost when Q is used to approximate P. So P represents the true distribution and Q represents the approximation of P. And there are two cases. In the discrete case, the KL divergence computes the expectation of the pointwise log ratio of probabilities presented by P and probabilities presented by Q. In the continuous case, it calculates the area. The example in the visualization shows two Gaussian distributions with slightly different means and variances. Suppose P is the actual distribution and Q is the approximation. We can see the difference between those distributions. The positive area when P is greater than Q and the negative area when P is less than Q. How to obtain a probability distribution? We can do normalization in data preprocessing step. So let's focus on document 1. There is a total of 12 occurrences or frequencies. So I'm going to divide each frequency by 12 and obtain this probability value. Now we will look at special cases of the KL divergence. So we already know it's non-negative, and when P equals Q, it's going to give us 0 because both distributions are identical. But what happens when P equals to 0 or Q equals to 0? For P equals to 0, the limit of P log P is going to be 0, so we're not going to get into any trouble. But the problem is when Q is equal to 0, it's going to get the KL divergence to infinity because now we're dividing over 0. To overcome this issue, we need to do smoothing. The most straightforward approach to do smoothing is to add a very small value, epsilon, or subtract it. In this example, the P distribution is missing the D value and the Q distribution is missing the C value. So what we end up doing here, we added an epsilon, then subtracted 1/3 from each probability, and we did the same for the C and Q. So now C equals to epsilon, and we subtracted 1/3 epsilon from everything else and applied the formula. As we mentioned earlier, the KL divergence has an information theory perspective, and it essentially measures the number of expected extra bits needed to code samples from P distribution using the Q distribution when the P distribution is not available. So when we take the expectation here, you can see how the number of bits to code samples from Q are separated from the ones to code P, and the result is always going to be greater than or equal to 0. One last note about interpreting the KL divergence from an information gain point of view. So it measures the information gained when one revises their beliefs from a prior distribution Q to a posterior probability distribution P. Sometimes it's called information gain achieved if P used instead of Q, or relative entropy of P with respect to Q. In summary, we covered KL divergence, what is it, and how to compute it.